Yeah, hi. We are watching. I don't even know where this is. What kind of page? Play crazy game. Yeah, probably it fits. Redefining energy brings Einstein closer to quantum mechanics. The new math does well with thermodynamics and black holes. Quantum relativity. We have two extremely successful theories, which seem to stand up to all experimental proofs. The theory of relativity explains things very well on the cosmic scale, while quantum mechanics explain things well on an atomic scale. Yeah. So, what's with the stuff in between and why they don't fit together in the first place? Why, you can't explain one world with two theories which don't intersect with each other in no way. The problem is that the two do not talk to each other, which shows us that there is something beyond physics that we learned at school. Or that we didn't learn at school. I don't know. Now, however, a trio of researchers from the University of Kyoto, Japan, has done work that brings the two theories together in a way that no one else has ever done. Yeah, it would be really cool if they would have shot the Large Hadron Collider into space, but I don't think that they did that. Hmm. Definition of energy that encompass entropy. I had to Google what means entropy. Since I'm not educated, I every now and then have to Google, and English is not my language, my first. And this is what Google found out. Physics, a thermodynamic quantity representing the unavailability of a system's thermal energy for conversion into mechanical work, often interpreted as a degree of disorder or randomness in a system. The second law of thermodynamics says that entropy always increases with time. Wrong. Lack of order or predictability, gradual decline into disorder. Where have we been? Definition of energy that encompasses entropy. In other words, chaos, if I get it correctly. Einstein knew the mathematical challenges well. He struggled to define energy and also mass in a way that recognized the law of energy conservation and covariance, which is the fundamental characteristics of general relativity, where physical laws are the same for all observers. Except for the suspicious ones. What the trio of physicists has now come up with is a new approach to this old problem, and they've done it radically. Changing the definition of energy so that it incorporates the concept of entropy, chaos. Although much effort has already been made to reconcile the mathematics of general relativity and quantum mechanics, and the team proposal results in an endearing simplicity. The solution is surprisingly intuitive, said Suichi Yokohama, staff member. Einstein's field equations describe how matter and energy shape space-time, and how, in turn, the structure of space-time moves matter and energy. Solving this set of equations, however, is notoriously difficult, like defining the behavior of a charge associated with energy momentum tensor, the problematic factor that describes mass and energy. It's the charge which gives things mass. The team noted that the charge conservation resembles entropy, which can be described as a measure of the number of different ways to organize the parts of the system. And here's the big difficulty. Conserved entropy defies this standard definition. Fuck it, let's continue. Energy conservation without symmetry. Chaos. The existence of this conserved quantity contradicts a principle of basic physics known as Noether's theorem, Amalia Emmy Noether, in which conservation of any quantity usually arises due to some kind of symmetry in a system. We propose a new class of vector fields to construct a conserved charge in a general theory of fields whose energy momentum tensor is covariably conserved. We show that such vector field always exists in a given field theory, even without global symmetry. We argue that the conserved current built from the asymptotically time-like vector field can be identified with the system's entropy current. Chaos current? A current of chaos. Yeah, sounds like quite oxymoronious to me. Surprised that other physicists have never applied this definition of energy momentum tensor. Another team member, Shinyue Aoki, said he is also intrigued that the general curved spacetime, a conserved quantity, can be defined even without symmetry. Thermodynamics and black holes. With the mathematical question resolved, let's go back here. Where's my pen? We propose a new class. So, a new class. Those mathematical questions which have been resolved, they were resolved by inventing some new thing, which is not resolving anything. On the quantum mechanics side, they demonstrated that their new definition of energy satisfies the first law of thermodynamics, energy conservation, for an isotropic system at a given temperature. Does this mean that it doesn't fit anywhere else? I don't know. On the relativity side, the team applied the new approach to observe a variety of cosmic phenomena such as the expansion of the universe and black holes. And I really hope they were wearing safety goggles, gloves, and a helmet when they were trying these new things. Like, as you would expect from scientists, they blew things up and see what went on. Or did they? I don't know. I bet they didn't. The calculations correspond well with the currently accepted entropy behavior for a Schwarzschild black hole. One of the three main mathematical solutions to explain black holes. And the equations show that the entropy density is concentrated at the singularity at the center of the black hole, a region where space-time becomes ill-defined and all physics collapse. Says, keeping the same framework well known to physics. All right. All physics collapses. Gaps in theory. Yeah. Recently we had cracks in theory, now we have a gap. Shout out to Andrew Hall. The equations and new definitions suggested by the trio are surprisingly intuitive as they point out but they are also not complete, with a few points still to be tacked on. For example, although entropy is always conserved in the situation they analyze, there are several ways to violate the conservation of entropy, changing the boundary under field conditions or violating the covariant conservation of the energy moment tensor. I have to agree, I have no idea what the energy moment tensor is, but I will figure it out what they mean by that. The three physicists recognize these gaps but claim they have not given up on them. We leave these interesting questions for future studies. More money. To close these issues, the trio says it hopes that its research will stimulate deeper discussions and that it will involve researchers from various fields, not only those who deal with the theory of gravity or the unification. Something's going on. Sorry for that. Not only those who deal with the theory of gravity or the unification of relativity with quantum mechanics, but also from all of physics, basic and most fundamental. What if everything we know about dark matter is totally wrong? It's really hard to somehow. I was thinking this now for quite some time. And I really want to somehow like share my thoughts, but they didn't wind up yet. It's basically about the relationship between knowledge and understanding. So it's hard to explain what I mean. That's why I still didn't make a video. But you can know everything about black holes. So it's basically knowledge. But what if everything we know about dark matter is totally wrong? Is that after all like just knowledge with no understanding? There aren't any black holes anywhere. But still, like the article I just read you before, it's, I don't know, yesterday? Today came out or something? I don't know. That's a screenshot from a video, Thunderbolt's project. It's about a year old. And you can, that there's much knowledge about there is no black holes or these kind of things, gravity, space-time crap, like which is much older than this 1 year. And if you want to know more, like check out Walt Thornhill and all the other guys from Thunderbolt's project. They can explain you really well. Like in my recent video, 75,000 bright black holes found. That's like, it doesn't make sense. Even though you would never have heard of a black hole. A bright black hole doesn't make sense to anyone. They probably know it, so they just find much more. Now we have 75,000. You have to believe, because we found so many. The amount doesn't really change, like the quality in many things, which is somehow funny. Because there's, like, according to those, like, there's basically a whole bunch of nothing in the black hole. It's like nowadays, or like today's science, it's just really big, but don't touch it. You get sucked in and you will never come out again. and it's really expensive too. But I will leave a link below to this video. You probably want to check it out. And yeah, I leave it here. Thanks. Bye.